Intuitively, you can think about it as going up a ladder. You can't put your feet in between the steps. So the question looks simple. Where's the catch? What are we trying to predict with the model? Can AI be used in quantum science? Hello, my name is Marcin Umiński. I work as a data scientist in DeepSys AI, and I also work as theoretical physicist at Nicolaus Copernicus University. While we deal with AI chatbots and computer vision on a daily basis, today I would like to tell you a different story. I would like to tell you about the common ground between the two worlds, about the link between quantum physics and AI. Let me briefly outline my plan for today's presentation. First, I would like to introduce you to some basic concepts of quantum physics. Then, I will tell you how we tackle our problems regularly. And then I would like to discuss some examples with you. But before we take the first step up this ladder or take a deep dive into the nuances, let me ask you a question. Can AI be used in quantum science? In academic research, the insight we gain while trying to solve a task is often more important than the raw results we obtain. And as such, AI-based methods can be often depreciated as perhaps limiting our understanding. On the other hand, universities are full of passionate scientists who are eager to play with new technologies. Although side projects fueled with raw curiosity often end up unfinished due to lack of time. Neural networks came with a bit of a paradigm shift a couple of years ago. Historically, when we had to deal with data, we fitted what we found out to a function we knew. With neural networks, we can fit the data to an unknown function. To explain why it matters, let me take you on a quick course to the basics of quantum physics in just under 5 minutes. Over 100 years ago, scientists discovered that particles in a microscopic scale behave somewhat differently than what we expected. The energies were a bit off. The particles described by the wave functions have their energies quantized. That is, the energies cannot have any values. The values available are discrete. Intuitively, you can think about it as going up a ladder. You can't put your feet in between the steps. Particles in quantum physics aren't in a one well-defined state. Instead, they are in a mixture of all possible states all at once, in a superposition, if you will. As such, their behavior is governed by probabilities. The wave functions, which have no physical interpretation on their own, encode all available information of a system. It describes the probability density. When we think of an electron, we don't think about a point in space. Rather, we think about a cloud of probability density. Let me present you the equation every quantum physicist knows the best, the Schrödinger equation. It states that the Hamiltonian, the total energy operator, acting on the wave function, returns the eigenvalues, the energies, or the bound-state energies, perhaps, the steps of the ladder. In this equation, the Hamiltonian is the question we're asking. The wave function is the object we are asking about, and the energies are the answers we are trying to find out. Now, it doesn't really matter if you're into quantum scattering, chemistry, if about spectroscopy or quantum computers. You need to obtain those values one way or another, the steps of your ladder, right? So the question looks simple. Where's the catch? The problem is that the Hamiltonian itself is uncertain, and the wave functions, the exact wave functions, are unknown. So take a look at the Hamiltonian. It incorporates all what's going on in the system regarding energy, like kinetic energy, internal energies, And here I highlighted the interaction potential. What it is, when two particles interact with each other, the interaction potential is a sum from one's perspective of van der Waals attraction and electrostatic repulsion. In this case, we can easily define the potential depth, the equilibrium distance. However, this is often too simplistic. In reality, we often need to deal with more complex situations. Two colliding molecules would have more degrees of freedom due to additional distances between them and angles. They can have like 6 degrees of freedom. In this case, we are talking about multidimensional potential energy surfaces. Quantum chemists spend a great deal of their time trying to compute them. Accuracy here is critical because it allows us to obtain results from the Schrödinger equation. Now, if it's so complicated, how do we manage to do it? The answer is we cut corners. We use approximations. For example, to solve the Schrödinger equation, one might use my favorite, the close coupling method. In this method, we solve an equation with a matrix, the close coupling matrix, that has rows and columns for each and every possible state. The on-diagonal items include the interaction potential, describe the internal dynamics of a state, and the off-diagonal elements are what enables mixing of the states. It is accurate, but the problem is it is computationally heavy. For example, when dealing with the wave function, we can use different approximations. In 1950s, the scientists noticed that, well, we may use the Hamiltonian to ask about a specific wave function. But if we don't know the wave function, we can take a different one. Ask about a different but similar object, perhaps with the same boundary conditions. And what we get here is a different answer, a different energy, but close one. We are trying to guess the wave function scientifically. The premise is that the closer our wave function is to the true one, the lower is the energy, and the better is our approximation. Now, how can we apply machine learning? There are various different approaches. Firstly, the black box. There are some physical features of a system. Every atom has a certain amount of protons, electrons, charge, mass, magnetic momentum. Perhaps we can use those and try to predict outcome directly. This is difficult, and we lack understanding of what's going on under the hood. There's this method of using unequal spacing in our precise calculations. When trying to compute the potential energy surface, perhaps we can just perform calculations in select points instead of a fine grid. And there are also methods like the decision tree, which are fully human comprehensible. These are the interpretable machine learning methods. Now, you may ask, what are we trying to predict with the models? Is this the Hamiltonian, the potential energies, or the wave function, or perhaps or the solution? The answer is it depends. Possibly everything all at once. So let me discuss some examples I selected with you. First, using neural networks for the variational method. I told you that we are trying to find a wave function that returns as small energy as possible. You may notice that this calls for using a neural network. We are trying to optimize the wave function, and the loss function is already defined by the nature. That is the energy. And there is the physical lower limit set on the available energy. The real energy of the ground state is the lowest you can go. So in the most simplistic way, this might be fully unsupervised learning. We are trying in each step to converge on a local minimum of energy, modifying the wave function. And thanks to this, we can then compare our models because uh, the values of energies are objective. We can compare models from methods. This is a well-studied case and well-documented one. A different example I would like to provide is using Gaussian processes with Bayesian optimization. So we generate uh, Gaussian processes, a set of random uh, plots, curves, if you will, that are normally distributed around some value. These are our priors. Then we condition them by observations, by exactly calculated or measured values in select points. And now we ask about the likelihood of a plot fulfilling those conditions. And then we use what's introduced by Bayesian optimization, the acquisition function. It points us to points of high uncertainty, and it shows where should we perform our next iterative calculation. This also handles a compromise between exploitation and exploration. We either focus on accuracy or broaden our search. And what's great is this requires no prior knowledge. This can be any plot. This can be potential energy or perhaps the bound state energies. Also, this is highly efficient. We can converge on an accurate plot with very few steps. Last example I would like to present you is the method called delta learning, which was popularized by the professor Pablo Drau. So instead of trying to predict uh, the value, we are trying to predict the difference, the delta, between values obtained from cheap but inaccurate methods and expensive, complicated, accurate ones. I found an example that relates to my field of expertise, where scientists just last year were able to substitute the results from a six-dimensional coupled channel calculations with much less time-consuming calculations and get essentially same results. And this model has been proven to efficiently reduce the errors obtained from, uh, from the cheaper, less accurate methods. Now, to sum up, I have talked with you about what we do in quantum physics. I have shown some methods we use and provided some example where we can use machine learning based methods without, what's important, sacrificing our understanding. These methods have been tried and tested, but they are not broadly used by scientists yet. It's important to notice that the meeting points between applied machine learning and physics do exist. We can mutually benefit. Machine learning specialists could contribute to scientific research, while researchers could take advantage of such collaboration. Because, well, when you have limited resources, you have to be very smart about the tools you use. Thank you for your time and see you next time.